Okay, so moving on to our next example, we look at KCl in water solution. So with KCl, you know that this is an ionic compound, and you know that it is soluble in water. So you know that when it's present in water, it breaks apart or dissociates into K plus and Cl minus. And we also have the water present, so we have H2O. So, when we look at this and we're trying to discern what intermolecular forces are present, we see that we have something that forms ions. And if we look at this molecule, if we look at H2O, we know that this is a polar molecule. It has polar bonds between the oxygen and hydrogen. And if we look, because it has these lone pairs on the central atom, we know that it has a net dipole moment. So water is a polar molecule, and we have something that forms these ions. So therefore, we know that one of the intermolecular forces present is our ion dipole-dipole force. Now, what else is present? Because we have our polar water molecule, we know we have London dispersion forces, we know we have dipole-dipole forces, and because we have a hydrogen, actually we have two of them, bound to an oxygen, we know we also have hydrogen dipole-dipole forces. In terms of strength, however, we know that out of the four, the ion dipole-dipole force is the strongest. If we move on to SO2, this molecule you do have to draw out. You can't just look at and discern whether or not it's going to be a polar molecule or not. So if we draw the Lewis structure, we have sulfur, there's 1 with 6 electrons. Oxygen has 2 with 6 electrons. So we should have 18 electrons in our structure. Sulfur is our central atom. We give our oxygens an octet, and since we know that they are not an exception, they want 8, so we give our oxygens 8 electrons. Then we look, out of the 18, how many have we drawn? And we see that we've drawn 16. So we put the remaining 2 on the central atom as a lone pair. Now, you've drawn all 18 valence electrons, you've given your oxygen an octet, but the sulfur does not have one. Therefore, you know, you've used all 18 of your valence electrons, that you have too few. So you know that you're going to have to form a multiple bond. And in this instance, it doesn't matter what lone pair from what oxygen you form the multiple bond with. So when I do that, I have now a double bond between one of my oxygens and a single bond. So I've used 18 of the valence electrons, both of the oxygens have an octet, and now my sulfur has an octet. So this is the Lewis structure for SO2. So now I need to determine molecular polarity, and I look and I say, okay, there are polar bonds because sulfur and oxygen do not have the same electronegativity. So because there are polar bonds, I know this is going to be possibly a polar molecule or a nonpolar molecule. I have to determine if there is a net dipole moment. So I ask myself those 3 questions. I say, do I have a different atom bonded to the central atom? And the answer is no, I have 2 oxygens. Do I have a lone pair bonded to the central atom? And the answer is yes, I have 1 lone pair on the sulfur. Therefore, this is a polar molecule. So since I know the polarity of the molecule, I know that London dispersion forces are present, dipole-dipole forces are present in all polar molecules. I need to check, do I have a hydrogen dipole-dipole interaction? And I see that I do not, so therefore my dipole-dipole force is the strongest. With the next example, we have actually one of the compounds very similar to what you will be testing. Actually, I believe you are testing this one. This is what's known as ethane. This is a compound you will be actually testing in experiment number 11. And the structure of ethane is a carbon bonded to 3 hydrogens and an additional carbon. So this is the Lewis structure for ethane. Now this particular molecule, even though it has polar bonds, is a non-polar molecule. So this is a non-polar molecule. There's no net dipole moment, which means that the only intermolecular force present within this molecule is London dispersion forces. So ethane, one of the molecules that you're testing for this experiment, you now already know is non-polar, and the only intermolecular force present is London dispersion forces. If we move on to HF, hydrogen fluoride, we see that we have a Lewis structure that looks like this, and we see that there is polar bonds present. Hydrogen and fluorine definitely do not have the same electronegativity, so it could be a polar molecule or a non-polar molecule. But with hydrogen fluoride, you know just by looking at it that there is going to be a net dipole moment where we have a partial positive on the hydrogen, partial negative on the fluorine. Therefore, you're going to have a polar molecule. So you would have London dispersion forces, dipole-dipole forces, and do you have a hydrogen bound to a fluorine, nitrogen, or oxygen? And in this case, you have one bound to fluorine. So you have hydrogen dipole-dipole forces present, which you know is the strongest out of the three. If we move on to the next example, if we draw the structure for this, this structure is what's known as ethane. And ethane is also a non-polar molecule. There's no net dipole moment, even though it has polar bonds. Okay? And therefore, the only intermolecular force present is what's known as London dispersion forces. So, we know that this has to be the strongest within the molecule. Question 14, if I draw this structure, it's given to you in the pre-lab questions. If we look at this molecule, we have to determine the polarity in order to determine whether or not this is in order to determine which intermolecular forces are present. And in this molecule, because there is what's known as a mirror plane or a mirror of symmetry, okay, or a plane of symmetry, because that's present, we have a non-polar molecule. Now, this is something that you will get into a lot when you get into organic chemistry. But for now, if you look, you see that you have this plane of symmetry where this side of the molecule is exactly the same as this side of the molecule. When that happens, you end up with a non-polar molecule. Therefore, in terms of intermolecular forces, you have London dispersion forces, which are the strongest. The same sort of thing applies up here with ethane. You see that the left-hand side is exactly the same as the right-hand side, therefore it is a non-polar molecule. But again, like I mentioned, this is something that you will go over when you get to organic chemistry. So we can talk about that a little bit later for these particular molecules. Now we have two remaining examples. We have CO2, and in order to determine the molecular polarity of this molecule, you do need to draw this one out. And so if we draw the Lewis structure, we have 1 carbon, 4 electrons. We have 2 oxygens, 6 apiece. So I should have 16 electrons in my structure. I know carbon is my central atom, surrounded by the 2 oxygens. I know I give a single bond from my central to both of my terminal. I know I give both of my oxygens 8 valence electrons. And then any remaining electrons I put on my carbon as lone pairs. However, I've used all 16, so if I look at this, both oxygens have an octet. I've used all 16 of my valence electrons, but carbon does not have an octet. So I know that this is an example of when I have too few valence electrons. So I know I need to form a multiple bond. So when I do that, I now have a double bond in between one of the oxygens. And I look, I've used 16 of my valence electrons. Both oxygens have an octet, but my carbon still does not have an octet. It only has 8. So I form another multiple bond where we now have 2 double bonds between our oxygens. So I look, both of my oxygens have an octet still. My carbon now has 8, which has an octet, and I've used all 16 of my valence electrons. So this is the Lewis structure for carbon dioxide. Now we have to determine the polarity of this molecule. So we have polar bonds, so that means we can either have a polar or non-polar molecule, but we have to ask ourselves, is there a net dipole moment? So do I have a lone pair on the central atom? No, in this case there's no lone pair on the carbon. Do I have a different atom bonded to the central atom? No, both of them are oxygens. If I look at the 3D, I know this is going to be a linear molecule, so I know that this is going to cancel everything out. There's going to be no net dipole moment, so I know this has to be a non-polar molecule. And since it's a non-polar molecule, I know that the only intermolecular force present is London dispersion forces. Alright, so moving on to the last example, we have selenium tetrachloride. So again, you're going to have to draw the Lewis structure for this one. And for selenium, there are one of them, it's in group 6. Chlorine, 4 of them, group 7. So I should have 34 valence electrons when I'm done. Selenium is the central atom surrounded by the chlorines. I draw single bonds. I give my chlorines an octet. And I look, out of the 34, how many have I used? I've used 32, so I put any remaining electrons on the central atom as a lone pair. And then I determine, is this a polar molecule? And I say, well, I definitely have polar bonds, so I know that this could be either a polar molecule or a non-polar molecule. And once I look at that, I say, okay, I have to ask myself those 3 questions. Do I have a lone pair on the central atom? The answer is yes. Therefore, we know we have a polar molecule. So we know that the intermolecular forces present are London dispersion forces, dipole-dipole forces, and we have to check, do we have any hydrogens bound to oxygen, nitrogen, or fluorine? And in this particular example, we do not. So we know that dipole-dipole forces are the strongest in this particular molecule. So with these intermolecular forces, it's very important that you're able to determine molecular polarity. So you have to be able to draw Lewis structures, and in some instances you have to be able to draw the 3D shapes. So make sure that you're very proficient in all of those things.